I'm Dr. Fred DePiro, and this video is on the node voltage analysis technique. This is part 2. Learning objectives included here are to apply the method of node voltage analysis, and this time including voltage sources, and as with the other topics in this area, to relate node voltages to branch voltages. Prereqs are an introduction to node voltage analysis, the ability to identify nodes, Ohm's law, and the ability to solve simultaneous equations. So recall that node voltage analysis is systematic and can be used on any circuit. First, we select a reference node as ground, shown here. The unknowns are the node voltages. You see here V1, V2. And then we use KCL to find a set of equations that we can solve simultaneously. Excluding ground, how many nodes are there in this example? There are 2 nodes. How many unknown node voltages are there in this example? Actually, there's just one. Thanks to this source right here at 111 volts and the fact that the negative terminal is connected to ground, we immediately know the node voltage V1. It's 111. V0, ground node, is assumed to be at 0 volts. So there are advantageous choices for locating ground relative to a voltage source. If we place ground at one side of the voltage source, this has a very nice benefit for us. It reduces the number of unknowns. Everybody likes that. Okay. Now, unfortunately, we can't always take advantage of this. For example, if there are multiple sources present. Here, one of the sources can have its terminal, say, near ground, but the other can't, just because they aren't near each other in the circuit. And another situation you might run into is if ground has been predefined in some manner so that it can't be relocated simply for the convenience of an analysis. Okay, so here we have this source, this voltage source, and neither side of it is at ground. Now, is this a concern? We're using KCL, so we're summing currents. So what is the current through a voltage source? That's a little bit of a stumper. We don't know the current through a voltage source ahead of time. So what could we do? Should we run away and cry? No. We need to use, let's think, we need to use the current of the source for KCL. We don't have that current, therefore we should define a new unknown. Okay, that sounds good. So to accommodate a voltage source with neither side grounded, we're going to define a new unknown. Here I called it IA, and since it's a current, I gave it a direction, of course. We'll keep the direction of IA constant through the analysis. Now, since we added another unknown, that means we're going to need to add another equation. So what information is out here in the circuit that hasn't been used yet? Okay, this source voltage. This source voltage, that 8 volts, hasn't been used in any fashion within the set of equations we've defined, and clearly that source is in between nodes 2 and 3, so that source is forcing a voltage difference between those 2 nodes. So which of the node voltages is larger, V2 or V3? Which one would be larger? It's going to be V3, the one towards the positive terminal of the voltage source. Now, one way you can set up an equation like this and make sure you get the signs right, think the larger node voltage is equal to the lesser known voltage plus the value of the source. So in this case, that's V3 is equal to V2 plus 8. Okay, so now we're ready to proceed with the analysis here. Steps are to first define ground, 2, identify the node voltages that we need to solve for, 3, in the case of a voltage source that doesn't have either side of it at ground, we need to define a new unknown. Here I called it IA. Then we can begin with KCL. Starting over here at node 3 and summing currents going out of that node. First contribution is going to be opposite the direction of IA, so we'll put minus IA, and then we have V3 minus V5 over 17, V3 minus 0 over 39. Right away we can substitute in the known value of node voltage V5, which is determined by this other source over here. Moving on to node 2. We have a current down from node 2 through the 56 ohm resistor, so that's going to be V2 minus V5 over 56. Another current down, V2 minus V5 over 19. And then we have a contribution as well associated with the current leaving the node and going through that upper voltage source. That's equal to plus IA. So we could substitute in for V5 with the numeric value associated with this lower source here. Okay, and then we add in our other equation associated with the difference in node voltages related to this upper source, and that gives us 3 equations with 3 unknowns. Solving those, you get these values for V2 and V3. Okay, our overall procedure here for node voltage analysis is shaping up. Now we've gone through examples that take us all the way through 1 through 5. The only thing left is just dealing with dependent sources, and that'll be covered a little bit later on in the course. Learning objectives for this, we're to apply the method of node voltage analysis, including when we have the case of voltage sources, and as before, to relate node voltages to branch voltages.